This is lecture 25, continuing our discussion of process synchronization. Let me motivate the example that we will discuss here, and this is a canonical example that we use to illustrate the issues that can arise. So to put it in some high-level context, suppose that we have A and B, typically in CS we call them Alice and Bob, and Alice and Bob, suppose, share a joint bank account. So joint bank account. And suppose here is Alice and here is Bob, and they work at different places, and they have, suppose, $1 to deposit, each one. And suppose that their total balance in their joint bank account is $10. That's how much money is in their shared data structure, aka joint bank account. Alice goes to some ATM machine that she uses, and at the same time, Bob goes to another ATM machine because Bob works at a different location, and they each then engage in a transaction to each thus deposit $1. So after everything is said and done, if all is executed correctly, this value, $10, should become $12. Then we know everything is sound. So suppose, again, just to give context, A goes through the ATM, which is a front-end device, and it uses network protocols over a network. So here's a network using stuff from CS422 to talk to a server. Suppose here is a server which is running some operating system. It could be Linux, which is very popular. And here is Bob, who is also connected to the network through this ATM machine, which runs software called network protocols that then again reach this server. So this server is the clearinghouse of all these transactions, deposits, and so on. And suppose the server here, so this server machine, has an application, a server process that's running. So this is a process. And this process is the one, suppose, that is going to manage the request coming in from A through the ATM, through messages reaching this guy, and the same for B. But it's the same process, let's call it S. And suppose that when the message from A arrives saying, hey, add $1 to the joint bank account, then to do so, this process forks, it creates a child process, say child C1, and then this child process executes instructions that update the joint bank account. When B's message arrives through this ATM and then reaches the same server S, then S forks another worker process, creates another child process, call it C2, and C2 then executes to update the bank account. And after both are completed, this dollar amount should now become 12. That's the general idea, just to motivate. So with that in mind, let's now look into this code in our slides, where here is process 1. So that's suppose the child process C1 that is executed due to Alice's request, and this is the child worker process C2. So process 1, process 2. And the code that they run is the same in the sense that they're just going to add 1 to the shared data structure, the shared bank account. And the shared bank account is here viewed. It's stored, of course, in a permanent storage device like disk. But suppose that for our purposes, because we are not discussing file systems yet, this is our main memory. That's been our computing model so far. And somewhere is our CPU. And this shared bank account, the balance on this shared bank account is a memory location X in this main memory. So here, before before C1 and C2 execute their work, this would be $10. So there would be the value 10 stored at address X. This is our variable. So under this setup, now suppose it turns out that the message from A gets there first. So this process P1 is forked first. What it does in terms of the actual machine instructions is copy X, the content of X, into register 1. So suppose this CPU has 2 registers and the machine code works with these 2 registers to perform the update. So there's this register, there's this register, like EAX, EBX, ECX in x86. So this guy now copies the content at address X, so that's 10, into register 1. So therefore, let me show this in blue. This is copied by the load. So this becomes 10. And then it performs an increment operation so that this then becomes 11. But after performing these 2 instructions, the scheduler is invoked. For example, C1 has used up all of its time slice, or for some other reason, and C1 is context switched out, which is perfectly possible. So we are not assuming that when process 1 runs, it disables all interrupts. We're just assuming it's just going to run this code. And after performing these 2 instructions, it just happens that the scheduler is invoked and the scheduler decides to context switch out this guy and context switch in this guy. So now, before this guy is able to execute its last and third instruction, we are now context switching to C2. And C2 runs the same code. So it loads X, which is still 10. So here, let me draw it in green. So it's still 10 here because we haven't yet updated. So it copies 10 into this register 2. So it copies it here. That is this instruction. And then it increments the content, so it becomes 211, like this guy. But here it's able to actually, let me move this guy here a bit. It's able to now update the shared data structure, in this case just the singular memory location X, with the updated value in reg2. So this third operation now being executed is going to copy the content of this register 2, which is 11, and it's going to now update by writing it, by moving it here. So now this 10 has become, under this operation, 11, because this was 11 here. So this process now is done. It terminates. And suppose next the scheduler runs and it decides, hey, let's run C1 again because C1 is not yet done. So C1, which was context switched out, is context switched back in, and it continues where it left off. So it would be after this instruction, which was the last instruction that it executed, which increased its register value reg1 from 10 to 11. So the next instruction is to copy the content of register 1 to X. So it would be copying this content here, which is 11, to X, the same shared data structure, the same memory location X, but it's 11, and here it was 11, so it remains 11. And then of course C2 is done, so this process terminates, and we would conclude the 2 transactions by Alice and Bob have completed, and this is their new balance. Obviously, this is incorrect because this balance should be 12, but it's only 11. And here, the reason why this is happening is that the individual instructions of these two processes are not being performed atomically. This guy was performed atomically by happenstance. But these instructions, these three guys, they were not. They were not atomically executed. Namely, after these two are done, this guy is interrupted, this guy runs, and this guy runs. If process 2 and process 1 don't share any data structures or have other dependence, this wouldn't matter. But because they are using, as we discussed in the last lecture, shared data structures. In this case, the most simplest form, which is a singular memory location. Even in this very simple case, it can here be seen easily because they are sharing this. When things are not updated in this atomic fashion, it's possible through interleaving of these instructions of processes that are sharing data structures, that the outcome, that the end result is not what is intended. It will not be the same as the outcome from executing these three things atomically and then executing these three things atomically. Because if these three instructions were all executed first, then it would mean that it would copy 10 here, it would increment it to 11, then it would store 11 back here. Then C2 runs, it reads from X, which now has 11 as the updated value. It reads it, it increments it, it becomes 12, and then it writes it back to X. Hence, it will be correctly 12. So all of this code is written under the implicit assumption that these would run without disturbance by other processes that may be sharing these shared data structures. And when that's not the case, then havoc can arise, as this example illustrates. This is also known as a racing condition. That is racing in the sense that these two processes, these two active guys, are time-wise in competition to access this X to read or write. And depending upon how that race unfolds, it's possible that the end result is what is expected, or the end result might actually be wrong. And all of this is influenced, as we see here, by what we discussed earlier, which is scheduling. So all of the stuff about scheduling, context switching, and saving state, all of this is the basis on which we can now consider process synchronization, under which we have to now worry about these racing conditions, which is really not easy to predict. It's in general non-predictable, it's unpredictable, it's non-deterministic. Because maybe the scheduler here is going to context switch out this guy after it executes this instruction. And then it executes these two. Or in other sequences that you can here clearly imagine. There are several combinations, but some of them it won't matter, for some of them it will matter. So it is this racing condition, which is non-deterministic, that we have to manage so that when we run these applications, this is software, P1, these two guys, C1, C2, these processes are just software, and we want to assure that they're going to run correctly, that is, as intended. And when trying to do so, it's not enough to just write this pure code and not worry about it we have to explicitly, when we are coding this, worry about racing conditions. And from the kernel's perspective, we need to make sure that when the app programmer is aware of these issues, which exist in pretty much all computing systems, except for cases where it's very, very trivial, or it's simplified, or it's been made to be only in one way. But in general, this is a very common situation. And app programmers who are competent better know about this issue, and they need to think about what can the kernel do for me? That is, what features of the kernel can I, the app programmer, utilize to prevent wrong outcomes from being reached by my application? This is the application. This is the server design. And so from the kernel viewpoint, that is what we're trying to do. That is, what features of the kernel. So here we know our layers, user mode, kernel mode, and we're exporting. So we are making visible to the user mode the API called system call interface. And so now the question is, what features do we add to the kernel and make available for use by the programmer? The user is our programmer, through the use of the system call API, so that these issues of process synchronization that can go wrong can be prevented, can be fixed. So that's our main concern here. So let's get rid of this guy and move on. So in terms of techniques, we are going to consider, as I noted earlier, two main approaches. One is using hardware support, and the other one is principally using software support. By software support, we mean using what is called semaphores. And by hardware, we are going to consider two methods. Interrupt disabling, that's something that you have already seen, because in Xenu, all system calls start by interrupt disabling. So hence in Xenu, we've been using that as our main mechanism to prevent data structures used by the kernel from becoming corrupted. So this is something that's already familiar to us, but we are going to now couch it into a more general problem. The second method is a spin lock, or in our case, we will just call it a T-set instruction. So this is all hardware support. This is mainly software support. So we need to go over these three steps. So interrupt disabling. Let's first start with that. So here, that's something that's already familiar to us. And so what we can do is look at this example of the code that we just saw. So this piece of code. And it is this piece of code that as a whole in database called a transaction, or it would be called a transaction. It is this piece of code that internally is going to read and write to the shared memory location. Of course, shared data structures, they live in our main memory. So in X, this guy reads from X, this guy writes to X. So it's these instructions, not all of them, but it is one or more of these instructions that are then going to operate on the shared variable. The same for this guy. These three instructions, same instructions, with different registers, obviously. And to protect, to facilitate orderly access to X. So orderly access meaning it is not subject to the whims of the racing conditions that I mentioned. Rather, it is determined by what the program intends it to be. So this is by intent, orderly access. So we want to make sure that this is done, these are done first, then these are done next, or this is done first and then this is done next, but not by interleaving these instructions. So that's what we will mean by orderly access in this context. And so the first method, which is hardware support, is interrupt disabling. So to stick with our x86 XENU example, which we know now reasonably well, we want to make sure that these three instructions, which are touching the shared guy, are executed atomically and nothing happens while these things are ongoing. And of course, in x86, it would just be a case of clearing interrupts, CLI, which sets the IF flag to 0. And then after this is done, then restore interrupts by setting STI, okay, let's see, STI, so here is STI, squeeze it in here, which of course is going to set IF flag of E flags back to 1. So it's going to set it back to 1. So we're going to wrap this code that touches the shared data structure by preceding it with interrupt disabling, that's specific to our hardware, and then interrupt re-enabling, again specific to our hardware. The fact that we restore interrupts and that we save interrupt masks, that we discussed already. Here we are focusing on what's actually going to happen at the end of the day, which is for this guy, set this flag to 0 and then reset it to 1. And this disables all external interrupts, which includes our system timer clock that we've been using. And we talked about two chores that we highlighted in the context of scheduling. We called them 2 and 2 prime. One is to wake up sleeping or blocked processes. The other one is to keep track of time slice depletion, so that if a process uses up all of its time slice, then that too is detected by the clock interrupt handling part of the kernel, which is the lower half of the OS. But by setting interrupts to 0 in our hardware, we are disabling these clock interrupts. So therefore, there's no processing of wake up that will happen and no processing of time slice that will happen. And it is these two guys that we saw in the earlier labs that you implemented that are then calling in XENUs its scheduler reschedule. That's the pathway. The other pathway was of course top down. That's through a system call. And in our case, the canonical system call that we are using that can block a process that makes a system call was our sleep system call, sleep MS. But obviously, in this particular case, this guy is not making a sleep system call. It's not doing a trap int to some interrupt number here that you did in the trapped interrupt case. There's none of that here. It's just regular instructions that we are trying to protect. And so, since this is not being done, and this cannot occur because we disabled all interrupts, which includes clocks. Who would then be calling the scheduler? So the scheduler won't be called. It implies that when this guy starts off first, this gets executed, no interruptions. The next instruction is executed, no such context switching possible. And then this is carried out. Everything will proceed atomically. And the same goes for this guy. So obviously here, by ensuring in this particular case through interrupt disabling, which prevents the scheduler from being called, and the scheduler is the one that calls context switching routines to context switch out the current process. But that can now not happen, which implies in this setting that process 1 will run these instructions atomically, and only when interrupts are re-enabled can 2 and 2 prime again happen and context switching can again arise. So this is quite clear and obvious in the case of a uniprocessor CPU. When you have multiple processors like CPU 0, CPU 1, CPU 2, CPU 3, then in general it's more complex because these two processes can run on different CPUs. So this guy is running C1 and this guy is running C2. And in this particular case, we need to make sure that when we are going to prevent the shared data structure from being corrupted, then just interrupt disabling will not be enough because this guy is already running on the CPU, and here is the main memory. So this is the main memory where X lives, the shared memory lives. And both CPU1 and CPU2 might access them because it's not a question of scheduling them on the same CPU. And so for this scenario, this way of doing it will not work. It will work for all processes that are sharing data structures should they be assigned to the same CPU. In that case, this methodology will work. So there are more complications that come into play when we have to consider multiple CPUs. And one of the methods that we will now discuss is the second method of using hardware support to achieve this atomic operation of these processes that are sharing memory, that are sharing data structures that are, of course, resident in main memory. That's the key idea. Also, one terminology, these instructions that are being protected, sort of quote unquote protected, meaning that we want them to run atomically. These instructions are also referred to as a critical section. So it is ultimately these instructions that are accessing by reading and writing to the shared memory location. If these instructions do not run, then we are okay. So therefore, we just recognize that to protect this shared memory, that's our goal. This should be subject to predictable orderly access even under racing conditions that are not predictable. So this piece of code called the critical section, or CS, is what's being protected. It's what is being allowed to execute atomically by adding code that precedes this critical section and adding code that follows this critical section. So to make this a bit clearer, what we're saying here is that here is process P1 and P2, and they're sharing some data structure, in our case X. This is the example, shared memory, to which they read and write, both of them. And here is the critical section code that we just saw, the simple three-liner that accesses X. And to make this critical section run atomically on our uniprocessor backend machine, we would just disable interrupts. By interrupt, we mean external interrupts. And then enable interrupts. And of course, in x86, the instruction is CLI and STI. The same exact thing is done by P2 because it runs the same code. So it does CLI and it does STI. This is extremely simple and it's very efficient because one instruction does it. One instruction before the critical section, one following the critical section. And we call these instructions that precede this code that is to be run atomically, and then the code that follows after we execute this code atomically, we call them in general prologue and epilogue code. So the idea is an app programmer who is going to be using our system calls to make this work, or this problem is solved just by doing kernel programming. So you need to make sure that kernel processes do not get into each other's way. So in both cases, the programmer, kernel programmer or app programmer, has this structure in mind where here is the critical section code that accesses shared data, and the programmer must ensure that it's preceded by this prologue code and it's followed by this epilogue code. In this case, the trivial instance of interrupt disabling, interrupt re-enabling. Same for this guy, CLI, then critical section, followed by STI. So it's always a case that you need to make sure that it's the programmer, the software coder, it is the programmer's responsibility to ensure that the code is coded correctly. It follows this format. Prologue code, in this case CLI, then the critical section code, and then epilogue code, in this case STI. Same here. It doesn't work if the programmer doesn't follow this rule. If the programmer is not competent or just forgets something or introduces bugs and forgets to put here, for example, CLI, just focuses on this code but doesn't put CLI here, then it won't work. It has to be put here for this code, which is the real code to run, to do its job properly. So for that reason, in this particular case, this mechanism is called mandatory, is called voluntary mechanism. Voluntary, which means if the programmer follows this coding approach, this coding format, then we can avoid those racing conditions leading to wrong output. On the other hand, if the programmer does not follow this format, then all bets are off. Hence, it's voluntary. What is mandatory? Mandatory is when it doesn't matter whether the programmer has or has not implemented their code correctly. Suppose, for example, we have a file that's being shared, and the file has been brought into memory, so it does sit somewhere. And we have two processes, P1, P2, who are now reading and writing, or trying to read and write to the file. In most kernels, in most operating systems, there are features available, and we haven't discussed file systems, so therefore this is something yet to come. But this object called a file, that's part of a file system that resides on some hardware, may have attributes. So this is features, attributes. And these attributes include a feature called lock. That is locking. So this is the object to be protected. And the object has an attribute, has a feature called a lock. And the lock can be engaged and it can be released. So here it's not the case where we have code that we are preceding with some code prior, prologue code, and code that follows this code called the epilogue code. And by making this code run atomically, we are preventing bad things from happening. That is the approach under this voluntary mechanism that we are discussing here. But the other approach is we are not following this approach. If it's available, we are going to utilize a feature of the shared data structure, in this particular case a file, as the primitive to lock. And when this file has been locked, say lock has been acquired by P1. Then when P2 tries to access this file, so it tries to open, read, write, these system calls will fail. They will return an error saying you cannot do that because this shared object has been locked by someone else. Only when this guy releases the lock, then can open, read, write by another process succeed. This is mandatory because P2, if P1 has locked this file, cannot access the content. It doesn't matter upon how P2's code looks like, whether it has epilogue code or not, it has no bearing on the issue. This is a mandatory state where no one else can access the content until such time P1 releases it. It doesn't depend upon the programmer of P2 having done his or her job right by adding this prologue and this epilogue code. Even if they didn't do it right, it doesn't matter. The lock is there and it will prevent for sure from other processes accessing the content. So that's the mandatory case. Here in what we're discussing, it's focused on these voluntary mechanisms. So always keep in mind, we are trying to here protect a piece of code, make it atomic, or behave as if it were atomic by adding some code here and by adding some code here. Prologue code and epilogue code. And if this code is properly added, because this is code, then we will achieve the correct result even under racing conditions. So keep that general framework here in mind. So we are now done discussing the first hardware supported feature, which is interrupt disabling. So number one, interrupt disabling, clear what we're doing. And in the context of Xenu, all Xenu system calls by default, so a Xenu system call we saw, let's call it ABC, so that's a Xenu system call. It starts by disabling interrupts, again using a mask, and I discussed why we do it for the programming nicety purpose, but at the end of the day we are disabling interrupts, and here we are enabling interrupts. And within this boundary, the actual code, the critical section code, occurs. In general, this code may be sharing data structures like the process table or some global variables of the kernel, and so we need to make sure that those are orderly accessed. And one methodology on our uniprocessor backend is using this methodology. So this was the prologue code, this was epilogue code, and this happened to be, as we are calling here, the critical section. The second method under hardware support, so these are both under hardware support, is an instruction called tset or test and set, also called spin lock. It has different names, but I'll be using just this tset notation because it's quite simple. We call it generally test and set. So this is hardware support. And the specific form that this hardware support takes, it varies greatly from one architecture to another. So here we are not going to focus on any one architecture, but we're going to see logically what this hardware support is aiming to accomplish so that the programmer, again, can achieve orderly access of shared data structures through critical section code that then runs atomically. That's again is always our goal here. So in the test and set case, tset is an instruction, but it's logic. What does it do? will be here described as if it were a function. So here is t set, and we don't care about types, etc. At this junction, it takes one argument s, an integer, and s is initialized somewhere, suppose at the beginning to 0. So somewhere this variable s is set to 0. And now this hardware support has this logical structure. So it accomplishes this software operation in hardware. That's the idea. So what does tset do? It checks if this variable s equals to 0, then what it does is it sets s to 1. So s was 0, now s becomes 1. And then tset, which returns an integer, it returns 0. If this is true. So if this is 0, it sets it to 1 and it returns 0. Very simple. Else, if this is not 0, then tset returns 1. Very, very simple. This is all that this guy does. So this hardware support in software performs this functionality. So how is tset utilized to protect this critical section? The way that it's utilized is, we are not going to be disabling interrupts here. So here, we are not going to be disabling interrupts, and of course enabling interrupts. Instead, our Prolog code is going to be a bit different. So it's still Prolog code followed by Epilog code. That's always the same format. But the Prolog code, when we are using tset, not interrupt disabling, is a bit different. The Prolog code in this example is going to be a while loop. So while tset with s is true, do nothing. So if tset returns 1, and it can return either 0 or 1, that's what this tset does. If it returns 1, this while loop will keep looping, and so you don't escape from this loop here. If on the other hand, tset does return 0, then of course this is false, and then it escapes from this while loop, which is the Prolog code, and the next thing to do is perform the first instruction, the first statement of the critical section. That's it. What is this Epilog code? The Epilog code is set this variable s back to 0. So somewhere s has been initialized to be 0. And now this is the code of P1. And somewhere else is the code of P2, DEF. And both of them share some common variable like x that we saw earlier in their critical section code. So this guy also has a critical section code. We are prepending it, we are preceding it with our Prolog code, which is, let me highlight this guy here in green. It's going to be while tset s do nothing. So if this guy returns 1, we are stuck in this infinite while loop. When this guy returns 0, then we are able to execute this critical section code. And after we are done, we set s back to 0. So the Prolog code and the Epilog code is again the same for all of the processes that are executing critical section code that are sharing data structures in main memory in our setting. So let's now consider what this buys us. So P1 and P2 are two processes that are running. By the racing condition, we can never be sure who runs first, who runs next, and whether after some number of instructions of P1, the scheduler then context switches this guy out and then context switches in some other process, which could be P2 or vice versa. We don't know the future. It's in general impossible to know. So this is the racing condition. But we want to be able to write code that's going to work under all possible racing conditions so that we have sound software. So let's see if this is going to work. So S is 0. Suppose P2 runs first. So P2 runs, P2 executes its code. It enters the while loop. It calls tset. It executes tset because this is a hardware supported instruction, but we are showing its logic in this functional form. So it executes tset with S, which is 0. Well, what does it do? S, if it's 0, S is set to 1 and tset returns 0. That's what it does. It does, of course, all of these things atomically. That's why we need the hardware support. tset, if you just code it as software, is obviously not atomic because it has to do here comparison, then it has to do assignment, etc., etc. These are a bunch of instructions, certainly not atomic. That's why you need to have the hardware support so that this logic, this functionality, which in general would comprise multiple instructions, are through hardware, here denoted test and set with a singular argument carried out entirely in one swoop, i.e. atomically. So going back to this guy, S was 0, this condition, it sets S to 1, returns 0. Because it returns 0, P2 does not get stuck in the while loop, it escapes the while loop. But suppose that after P2 then escapes the while loop, it runs the code. And this code, suppose, is comprised of 10 instructions. 1 here, 2 here, 3 here. So suppose there are 10 instructions. But after P2 has executed half of the instructions, so it's in the middle here somewhere, the scheduler intervenes because we have not disabled interrupts. Interrupts are still enabled here. The scheduler intervenes and context switches out P2. So this is context switched out while it's in the midst of doing its critical section code. And suppose the scheduler decides by happenstance to context switch in P1. Well, P1 is running. P1's code is this prolog code before CS, which is the same. While tset S, just loop. But what is S now? S is now 1. So S is being called with 1. Before it was 0, now it's 1 because this guy made it so. So what does this code do? Now it's 1. So it's not 0, it's 1, else it returns 1. So tset returns 1. So the while loop is stuck. It keeps looping, which means it calls tset again. It executes tset again. But S is still 1. So same outcome. It doesn't hit this condition. It hits the else and returns back to 1. So it keeps executing tset within this while loop, and it can never proceed to execute this code because it's stuck in this infinite while loop. Until when? Until this process P1 has depleted, has used up all of its time slice. Right? Because when this guy has used up all of its time slice, then the scheduler again is involved, because we talked about how the scheduler is invoked by the kernel, upper half or lower half. And so this is one of the conditions. And it could be that after this guy has consumed its time slice, its priority is lowered, and suppose by happenstance again, P2's priority is higher than P1. It's still ready to run. It was forcefully here taken off. So P2 resumes running. What's P2's code? It was in the middle of its critical section, so it continues from here. So it executes the remaining instructions of its critical section, and then after it's all said and done, it sets S to 0. And then it terminates or does something else. But the key thing is, it has reset S to 0. And at some point, the scheduler, hopefully, is going to context switch in P1 again and resume where P left off. But where did P leave off? Inside this while loop. It was stuck executing this hardware-supported instruction tset. But previously it was with value 1. But now the value has become 0 again. So now P1 executes tset with argument 0, with operand 0. So we know what happens when it's 0. It's this condition. S is again set to 1, and then it returns 0. So it returns 0. It escapes the while loop. It's able to execute the instructions of the critical section, and then at the end, it's going to set S back to 0. So if there was a process P3 who came along, who wanted to run some critical section, and it also had a while loop, T set S, like so, and then S0 here, always the same structure, always the same format. P1, P2, P3, they're all part of the same app whose critical section are sharing a common data structure. So they all follow this same format. They must. It's of course voluntary, because the programmer better put this while loop here and better put S equal to 0 here, along with coding this code. Same for this guy, same for this guy. If the programmer skips this, then all bets are off. You just execute this code that then accesses X, not in an orderly manner, and might corrupt the value, as we saw earlier, under various racing conditions. So this only works under this voluntary mechanism, or this is a voluntary mechanism that must be followed for process synchronization to achieve its desired result. So in this case, if P3 comes along after P1 has already entered into its critical section and it was context switched out in the middle of it, then same thing happens to P3. P3 will be stuck in its while loop until P1 completes executing its critical section and resets S to 0. It's only then, when P3 runs next, that it will escape from its while loop. So therefore, these critical sections will run atomically one after the other. They cannot intermingle. We say interleaving. So the instructions of this code, this critical section belonging to P1, P3, and where is P2? P2, they are executed in one lump. They never are mixed together. They are never interleaved. And that is achieved by this technique called tset. Why hardware support? We just mentioned. So if we compare these two methods, interrupt disabling and this test and set methodology, with test and set, if you have two CPUs, so CPU 0 and CPU 1, and they are sharing here this main memory, this is our memory, and this is our variable X, and they are running P1 and P2, and their critical section code can read write to X, and you want them to run atomically, like we just said. Well, they can just perform this technique. Unlike interrupt disabling, which in this case would not work because their P1 is already running on the CPU, P2 is already running on this CPU. In this particular case, this guy or this guy, P1 or P2, will first execute tset, So that's the racing condition. So P1 or P2 will first execute this atomic T-set operation with S equal to 0. And only when S equals to 0 does T-set return after setting S to 1. So either P1 wins or P2 wins. If P2 wins, then P1 will be stuck in its while loop just forever. So it's going to waste the CPU cycles of CPU 0. That is, if there are other processes, P6, P7, P100 that are ready and they are needing to run or they are wanting to run on CPU 0, they don't get to run on CPU 0 because P1 keeps calling in its while loop T-set with S1 because this guy won first, so it set S to 1, but this guy, of course, was able to escape its while loop and enter into executing its critical section code. So this guy is busy waiting on this guy to release, quote unquote, this lock. So S can be viewed like a lock. This guy is this guy has acquired this lock S. It's now executing this code, but the other guy, it's running on a parallel machine on a different CPU, but it's doing work that is not super productive because it keeps calling T-set, and this T-set will keep returning 1. Until when? Until P2 running on this other CPU reaches the end of its critical section code and sets S back to 0. So this is P2. So it finishes running all these instructions, and then the last thing in the epilogue code is set S to 0. And when S is set to 0, then next time this guy performs T-set, it will actually perform this condition and be able to escape from the while loop because it returns 0, of course, after setting S to 1, so that any other guy who comes along and is trying to again win this lock is going to lose out because now P1 is going to be the winner because P2 is done with the lock. So whether you call it lock or not, that's not so important. The point is it's a resource that one or the other will acquire. We cannot know by racing condition who wins, but one of them will win. Both of them cannot win. Both of them cannot lose. There's one winner and everyone else. So there's one winner, P2 is the winner, P1 and P3 are the losers. And after P2 then gives up the lock because it's done with its critical section, then the guys who are in their own respective T-set loops in these while loops, they then by racing conditions. So we cannot know who among these guys is then going to get S next because it depends upon scheduling, it depends upon where in the instruction set, because while is a bunch of instructions, each process was, so it all depends upon timing under racing conditions. So it's not deterministic, but one of them will win. Suppose P3 wins, and then P2, P1 is still out of the picture, and P3 is running its critical section. P1 is still engaged in its while loop with a T-set. And when P3 is eventually done, then hopefully P1 can acquire this S and then complete. And there's a sequence of operations where the critical sections do not get intermingled and they are executed in this linear fashion. And when we compare these two hardware supports, the pros and cons are, this guy is of course special hardware support beyond interrupt disabling. And this is here explained logically, but making this thing that's logical be supported by hardware is highly non-trivial, but it can be done. When you have it, then on multiple CPUs, the good thing is it can then do things that you cannot do with interrupt disabling. The bad thing is that this is wasteful in general, because if this guy is now running its critical section and the critical section takes a long while, then until it reaches the end and it sets S to 0, for all this time, all of the other processes that could potentially run on the CPU, which is just keeping running, executing tset, is going to be not productively used. We could have, for instance, context switched out this guy and context switch in P7 so that the CPU is more productively utilized. And when P2 is done, it relinquishes, it's done with its critical section. And if you can notice that, then you may context switch in P1 so that P1 then can execute its critical section. And that is what our software support will allow us to do. So that's why in general, the software support based upon semaphore is in general the preferred method, and we will discuss what that is. Because both of these methods have their limitations. And of course, interrupt disabling even on a uniprocessor CPU. So we have one CPU like our Galileo backends. It's very disruptive because you're going to now lock down the system from having all external interrupts being silenced. No clocks ringing, no packet arrivals being handled. The only thing that happens is to run the code that runs with interrupts disabled. In Xenu's case, for example, it could be a system call. But let's take Linux or Windows as an example. It doesn't matter. The issues, they are common to all modern operating systems. So suppose in Linux, we were to implement a read system call. Of course, this is the wrapper. You know that this is just a wrapper. This is the entry point that traps then to the actual system call. But with that in mind, let's suppose that this is our system call code in Xenu. And what this code does is it disables interrupts, and then it does its stuff, and then it enables interrupts. Suppose this is the structure. Let us say that this were the structure that is being used by Linux to implement the read system call that you would have seen from system programming. This kind of sounds reasonable, and it may be reasonable because this is really super efficient in general, or its essence is one instruction, CLI STI for x86. But this makes sense if this code is short, if there are only a few instructions here. Then this is really a great way because you disable interrupts for a very brief period and you make sure that on this uniprocessor system no one else can squeeze in. You do your work and then you re-enable interrupts. So you're able to perform these operations atomically. Great. But this operation need not be short in general. Let's take read as the example. Read says read from some descriptor, from some device that's being mapped to a file whose handle is a descriptor, to where? To some buffer, to some user buffer. How much? Suppose it should copy 10,000 bytes. As an example. Well, this guy will need to copy 10,000 bytes from some buffer inside the kernel to this buffer buff that belongs to an application, to a process. The copy cost takes as long as the number of bytes that you specify here. If it's only 3 bytes, easy. But if it's 300, it'll take 100 times longer, etc., etc. So therefore, for some system calls, which can take actually quite significant time, and these are referred to as slow system calls. And there are a bunch who fall under this category of being slow system calls. They can take a while to finish. For those system calls, this methodology of interrupt disabling and interrupt re-enabling, that is this hardware support number one, is not viewed as a viable approach because you would be spending too much time here in this critical section with interrupts disabled. You can make the OS run correctly in the sense of not corrupting data structures, but it would have other very negative side effects, such as not being able to handle clock interrupts that may be important. Maybe you need to wake up a super important process, but the clock is silenced. Packets are coming in, messages are coming in over your Ethernet interface, your Wi-Fi, Bluetooth, all of them are being silenced. And these messages may be very important. And maybe behind this packet is another packet. These buffers can only store so many packets. If you keep disabling these interrupts, these packets that come in later, they will be discarded. We talked about drop tailing. So the damage that can ensue if you disable interrupts can be significant. And the damage can increase, in general will increase, the longer interrupts are disabled. So this methodology of interrupt disabling is valid if you know that your critical section is short. Then this is a good method to actually employ. If that's not the case, it is not the way to follow. So TSAT, we said, in the case of multiple CPUs, has its own limitations, and so altogether we are not happy with the hardware-based solution alone, and we now are going to study the software-based solution or using software support called semaphores. So we'll continue here next time.